Okay, now we're going to finish up this problem. So the maximum weight as a function of distance between supports. So now we're going to hold the thickness and the width constant, and we're going to vary that distance, d. So Perry chose boards that are 1.5 inches thick and 2 inches wide, and measured the maximum weight that the boards of different lengths would hold. Perry obtained the following data. You can see it in that table. The distance d in feet. So the different lengths of the boards, 1 feet, 2 feet, on up to 6 feet, and the weight that they can hold. So if you look at the weight, it's decreasing. So it looks like the longer the board is, the less weight it can hold. So it looks like it's going to vary inversely this time. So example 3a, use the converse of the fundamental theorem of variation to determine how m varies with d. Then find the constant of variation k and use it to verify the relationship between m and d. So we're going to select 3 data points this time. We want d1 and m1 and d2 and m2, and we want the d2 to be double d1. So if we pick d1 and m1, we do 1 and 2, 12. I just picked the first 2 data points on that table, and we want d2 to be double that, so we're going to do 2 and 106, which is the second set of data points, because 1 times 2 is 2, so the d value is double. Now let's compare our m values. So m2 over m1 equals 106 divided by 212, and that's half. So it looks like as our d value doubles, our m value decreases by half. Now let's do d3 and m3 and d4 and m4. Okay. We're going to pick 1 and 212 again, because we like those numbers, for d3 and m3. For d4, we want a distance 3 times as long as d3, so we're going to do 3 and 71, because 1 times 3 is 3. So now let's compare those m values. So m4 over m3 equals 71 over 212 equals about 1/3. So as the distance triples, the max weight is divided by 3. So m varies inversely as d, and we could write it as m varies inversely as d. That would be our general variation equation. And now they want us to find that constant of variation, that k value. So step 1 is writing the equation. Step 2, let's plug in some points to solve for k. And we're just going to use those first set of points. So if m is 212 when d is 1, then k equals 212. And then let's figure out if that works for the rest of the points. If our k is 212, it should work for all the rest of these points in the table using this constant, or using this variation equation that we just wrote. So let's pick another set of points. Let's do 5 and 42. If we have m equals 212 over d, m should equal 212 if we're using the 5 and 42 divided by 5. That equals 42.4, which is really close to that 42. So that definitely looks like that works. Okay, let's practice with another problem. Example 3b. Using the data given in this table, use that converse of the fundamental theorem of variation to determine how r varies with s. Find the constant of variation k to verify the relationship between r and s. Well, let's look at what's happening to r. R is increasing, so it's going from 1 to 6, and s is decreasing, it's going from 350 to 58. So it looks like it's going to be an inverse variation. We just don't know if it's going to be having anything, if it's going to be squared or not. So that's the only part we're trying to figure out now. We can tell that it's inversely related. So let's select some data points again. We'll do S1. Oh, and this should be, let's rename these. This should be S, and that should be R. They had them backwards. So we'll do S1 and R1, and S2 and R2. We'll do 1 and 3 and 350, just to make it easy. So when S is 1, R is 350, and we'll do 2 and 175, because we want our S value, S2, to be double S1. So that's why we pick that S2 to be 2. Okay, so if S2 is double S1, then let's see what happens to our R values. So R2 over R1 equals 175 divided by 350. That is 1/2. So when S is doubled, R is 1/2. So that looks just like an inverse variation relationship. Let's test it again with another set of points. Let's do S3 and R3 and S4 and R4. And this time we want S4 to be triple S3. So if we pick 1 and 350 again, we want S4 to be triple that S3, which is 1. We want 3 and 117. So now let's compare R4 and R3. 117 over 350, which is about 1/3. So as S is tripled, R is divided by 3, or 1/3. Okay, let's test it with, well, let's write our general variation equation, get our constant K, and then we'll test it with some other points. So we can say R equals K divided by S. That's our inverse variation relationship. Let's plug in some points to solve for K. We'll do the first one again, the 1 and 350. So when R is 350 and S is 1, this should be 1, then K equals 350. Let's write our equation then. We could say R equals 350 over S. And that's an S, not a 5. Does that work for everything? So let's test this last set of points here, the 6 and 58. So R equals 350 divided by S, which is 6. R equals 58.33, which is really close to that 58. So you could keep testing all the points to see if it works, but that should be pretty close. So our K value is 350, and our general variation equation is R equals 350 divided by S. So if we summarize Perry's results, this is what happens. So M varies directly as W and the square of T, while M varies inversely as D. So we could write it as M varies directly as W and the square of T, and it varies inversely with D. That is our single formula, and we're going to learn more about that in lesson 2.9. We're going to combine things and write one single formula. So it's called a combined and joint variation. So if we talk about this, it says the greater the width and thickness of the board and the shorter the distance between the supports, the more the weight the board can hold.